Welcome to The Explainer. Today, we're diving into the incredibly cool world of aircraft synchronous data transmission systems. Now, I know that sounds like a bit of a mouthful, right? But just think of it as an invisible string. It's this magical electrical tether that flawlessly connects the massive roaring engines on the wing directly to those quiet, vital instruments inside the cockpit. So let's jump right in and decode how this amazing technology actually works. To really appreciate the solution, we first need to look at the real-world problem it solved. Picture the very early days of flight. You had twin-engine aircraft where physical, mechanical cables connected the engine to a dial. Honestly, in some early planes, they literally just mounted massive dials directly on the engines right outside the window so the pilot could read them. It's wild. But as airplanes got massive, how on earth did pilots read dials for engines that were completely out of view? Those old mechanical cables simply couldn't stretch far enough without massive friction or just snapping altogether. And that physical wall, that's what paved the way for a revolutionary leap: electrical transmission systems. So, here's our roadmap for this explainer. First, the aircraft measurement problem. Second, direct current systems, focusing on the Desynn. Third, transformers and induction. Fourth, alternating current synchros. And finally, advanced synchro types. Let's get to it. Section 1. The aircraft measurement problem. Okay, so as planes grew in size and complexity, relying on physical, mechanical linkages for measuring things like pressure, temperature, and fuel levels became totally impossible. Electrical data transmission absolutely had to step in and save the day. And that brings us to the core concepts of our whole explainer today. A synchronous system is officially defined as having a transmitter at the source of measurement and a receiver used to position the indicating element. Whether the system uses direct current or alternating current, it's always relying on this fundamental relationship. The transmitter feels a change, let's say a spike in fuel pressure, and the receiver mimics that exact change on a dial for the pilot. They are perfectly synchronized. Section 2. Direct current systems. The Desynn. Let's look at how this was first pulled off using one of the earliest electrical setups widely adopted in aviation. The Desynn system basically takes three forms. You've got rotary motion, linear motion, which is also known as the micro-Desynn, and the slab Desynn. Now, while they're used for different things, from fuel levels to pressure indicators, that rotary motion arrangement is the absolute foundation that the other two completely build upon. So here is exactly how that basic rotary Desynn system does its thing, in 3 steps. First off, direct current gets applied to a toroidal resistor, that's just a circular resistor, via 2 rotating wiper arms that are physically attached to whatever mechanism you're measuring. Second, this resistor is tapped at 3 points, spaced exactly 120 degrees apart. As those wipers move around, the resistance between the wipers and those 3 tapping points shifts, which creates different electrical potentials. Third, those varying potentials shoot over to the receiver, generating shifting magnetic fields that physically pull and align a permanent magnet rotor to match. Boom, synchronized. All right, let's visualize this invisible string. Check out the schematic right here. Over on the left, you've got the transmitter with its positive and negative wiper arms sweeping across that circular toroidal resistor. You see those lines labeled 1, 2, and 3? Those are your tapping points, carrying the current all the way over to the receiver on the right. Once inside the receiver, those currents flow through a star-connected 3-phase winding. This essentially creates an electromagnetic compass, forcing that little north-south permanent magnet in the center to instantly whip around to the exact same angle as the transmitter arms. But you know how it is, engineering never stands still. The basic Desynn was great, but it had its limits. For tiny, linear movements, like really slight pressure changes, they engineered the micro-Desynn. This used 2 straight parallel resistors instead of a circle, just to magnify those tiny inputs. Then came the slab Desynn. See, the original circular resistor produced this kind of jagged, sawtooth waveform of resistance, which caused slight friction and cyclic errors. The slab Desynn brilliantly fixed this by modifying the resistor's shape to produce perfectly smooth sinusoidal waves. It was a massive upgrade in accuracy. Eventually, though, as aircraft kept advancing, these simple, direct current Desynn systems just weren't enough. Aviation needed something significantly more robust, capable of way higher accuracy, and capable of integrating with early flight computers. This triggered the big shift from direct current to alternating current systems. The whole industry moved toward AC setups, which are broadly classified under the generic term synchros, though you might recognize them under trade names like autosyn or cellsyn. Section 3. Transformers and induction.
Okay, quick detour into some fundamental physics, because to truly grasp how an AC synchro works, we need to talk about the secret sauce behind all AC systems: electromagnetic induction. This is simply the process of inducing a voltage, an electromotive force, within a conductor just through its relative movement with a magnetic field. When you run alternating current through a coil, it creates a magnetic field that is constantly expanding and collapsing. If you place another completely separate coil right next to it, that moving magnetic field actually induces a voltage in the second coil. This beautiful property is called mutual inductance.
You can see that exact concept playing out right here with a basic transformer. On the left side, we have an alternating voltage applied to the primary winding. That alternating current sets up an alternating magnetic flux that flows right through that square laminated iron core. That flux then passes through the secondary winding on the right side, magically inducing a voltage without a single physical wire connecting the two sides. And the really cool part? The ratio of the voltages is perfectly proportional to the ratio of the turns of wire in each coil. This specific physics principle is the absolute beating heart of the synchro systems we're about to explore. Section 4. Alternating current synchros. All right, physics lesson complete. Now, there are 4 main groups of AC synchros used in flight instruments, and they are classified completely by their function. We've got torque synchros, control synchros, differential synchros, and resolver synchros. We are going to break down exactly what makes each of these unique, starting right at the foundation. Starting with torque synchros, these are the simplest form of AC synchro. Think of them as a much more advanced AC version of that Desynn we looked at earlier. Their main job is to physically turn a dial. Both the transmitter and the receiver have a spinning rotor inside a stator with 3 windings. When both of those rotors are sitting at the exact same angular position, equal and opposite voltages are produced in their respective coils. Because they are equal and opposite, they just cancel out. No current flows through the connecting lines. We call this perfect state of balance being at null. But the second the transmitter moves, that balance breaks. Current rushes through the lines and it creates a magnetic torque that physically forces the receiver rotor to match the new position and return back to null.
Now, control synchros take this up a notch. Instead of wasting energy physically wrestling a pointer on a dial, they're designed to produce an error voltage signal in the receiving element. Say a central air data computer needs to know the plane's airspeed. The control synchro doesn't twist a mechanical dial. Instead, any slight misalignment between the transmitter and receiver generates a tiny, incredibly precise voltage that is perfectly proportional to the error. That voltage gets sent to an amplifier, fed into a 2-phase motor, and gently drives the system back into alignment. It's all about providing precise data logic rather than brute mechanical force.
Section 5. Advanced synchro types. This is where we get into some seriously clever engineering. Look at how this technology scales into complex mathematical operations using literally just wires and magnets. Here we're introducing a third piece of the puzzle, the differential synchro. This sits right in the middle between the transmitter and the receiver. In aviation, sometimes you need a single instrument to show the sum or the difference of 2 completely separate measurements. By wiring this uniquely wound differential synchro into the middle of the circuit, you can mathematically modify those magnetic fields. If the transmitter turns 60 degrees clockwise and your differential synchro is turned 15 degrees clockwise, the receiver will naturally output exactly 45 degrees. It is literally doing subtraction and addition purely through that invisible string of mutual inductance. Next up, the mathematicians of the group, resolver synchros. These are heavily used in automated flight directors. The entire function of a resolver synchro is to convert alternating voltages, which represent the Cartesian coordinates of a point on a graph, like your x and y, into a shaft position and a voltage, which represent your polar coordinates, so an angle and a distance. It pulls this off by using windings arranged in what's called phase quadrature. That's just a fancy way of saying the windings are mounted perfectly 90 degrees apart from each other. Let's trace the actual math on the circuit diagram. Because those stator windings are offset by exactly 90 degrees, they capture different fractions of the magnetic flux as the rotor turns. The voltage across one winding represents the cosine of the displacement angle, while the voltage across the 90-degree winding represents the sine of that exact same angle. By measuring the amplitude and phase of these 2 voltages, the aircraft's computers can instantly pinpoint exact angular displacements. It is literal trigonometry happening purely through electromagnetic fields. How cool is that?
Finally, we gotta talk about the Synchrotel. This one is a highly specialized, very low torque control transmitter. Think about it. If you're measuring extremely delicate air pressures for something critical like an altimeter, you cannot have heavy metal rotors dragging the whole mechanism down with friction. The Synchrotel solves this so elegantly.
Instead of a solid core winding spinning around, it uses a fixed coil and this completely hollow, super lightweight aluminum cylindrical rotor that's sliced at an oblique angle. As this feather-light angled tube rotates, it cuts through the radial magnetic fields just enough to induce a measurable, mathematically perfect sinusoidal voltage, without putting any physical strain whatsoever on the delicate pressure sensors it's attached to. So, wrapping this all up, the biggest takeaway here is this. What started as a desperate mechanical need to just read a dial on a wing engine evolved into an incredibly elegant, highly advanced network of electromagnetic communication. Now, obviously, today's modern aircraft are packed with modern microprocessors and digital fiber optics, but it leaves us with a really compelling question. How do these legacy electromagnetic invisible strings, these foundational principles of nulls, resolvers, and mutual induction, continue to shape the fail-safe architecture of today's hyper-digital fly-by-wire aviation? It's something truly incredible to think about the next time you're looking out an airplane window. Thanks so much for joining me on this explainer, and keep your curiosity